Hello everyone, welcome to lecture number 4. Topic for today is called infinite limits and vertical asymptotes. It's basically the same topic. We're gonna see why. Just to put this into context, what we have talked about so far is cases where you try to compute a limit and at least one of the one-sided limits gives you an actual number. And this time we're gonna be talking about cases where it gives you the numbers infinity or minus infinity, which technically you should not call numbers, more like symbols, but let's see how that works. And we're gonna start by saying just what this word means, asymptote. So an asymptote of the graph of a function, or you could just say asymptote of the function, is a line that, informally speaking, the graph of the function approaches, which means tends to become tangent to. And it's not really a tangent line because you're going to see the graph actually doesn't touch that line as it approaches that. So I'm going to just be drawing a few examples here. So first of all, horizontal, which means this direction, or slanted asymptotes can only happen as you take x to plus or minus infinity. So for example, if you imagine a graph of a function that looks like this, and usually you're going to see these dotted lines to indicate that the graph is trying to approach a certain direction, both as x is going to negative infinity and also as x is going to positive infinity. So you can see here examples of one horizontal asymptote and one slanted asymptote. And as I said, these are only happening when x is growing large in size, either to plus or minus infinity. And of course, not all functions will have this type of behavior. You can have functions like e to the x or x squared, functions which actually grow without actually trying to approach a line. So e to the x is an example of a function that has only one horizontal asymptote. And it's kind of hard to draw in here because it would be the same as the x-axis. As you can see right here, as x is approaching negative infinity, the graph of the function actually is becoming more and more horizontal and never crosses the x-axis. So x, it would be the line y equals 0, which is this horizontal line. The x-axis is a horizontal asymptote of this function, e to the x. However, on the other direction, this graph, if you were to extend it, you would see that it actually is not approaching any direction. It just tends to become more and more vertical. But it's not like it's approaching a line. It's not like it's going to stop somewhere and become vertical there. It just keeps going. So there is no line that it's approaching on that direction. But this first example here, horizontal and slanted asymptotes, is going to be the topic for next lecture. Today, we're focusing on vertical asymptotes. So let me talk about that now. And as you can see written in here, vertical asymptotes can only happen as x approaches a number a. Which makes sense. Like if you cannot imagine a graph approaching a vertical line as x goes, for example, to plus infinity, because if you want to approach a vertical line, that means your graph is stopping there. So your x would not be going without bounds. So if you try to imagine examples of graphs with a vertical asymptote, it could be something like this, a graph that has a bounded domain, for example. Let me draw this in red, well, the asymptotes in blue. Let's imagine like this is the number -4, and here is the number 3. You can imagine a graph that's doing something like this. You see that it's trying to become more and more vertical as x approaches both -4 and also 3, which means that those lines, x equals -4 and x equals 3, are vertical asymptotes. And we're going to be able to describe this in terms of limits. In this graph, if you look at the limit as x approaches, for example, -4 from the right, it can only approach it from the right because I'm not drawing the graph on the left side. There is no f on that side. But on the right side, if you look at this limit, we're going to be saying that it's equal to plus infinity. And similarly, as you are approaching 3 from the left, we're going to say it's equal to minus infinity. What those mean is just that f is growing without bounds, and positive here and negative here. So it's not approaching a limit, but it just keeps growing. So this is the idea that connects infinite limits to vertical asymptotes. So for the next of today, we're just going to be talking basically about infinite limits. Only on the very last slide, I'm going to connect this idea to vertical asymptotes again, which is just, we're talking about that because it helps us draw graphs of functions. It helps us to understand when a graph is approaching a line. So let's talk about infinite limits. This is the moment where you pause the video and you copy this down in your notes. It looks scary, it's like long definitions here, but you'll see it is basically very intuitive. So I'm going to be talking about them now. Infinite limits just means either plus or minus infinity. So the first definition here is talking about an infinite limit of plus infinity. Here's what it says. You're going to have a point A. So suppose f is defined near a point A, which means on both sides of it, but not necessarily at the point. We say that the limit of f of x as x approaches A is infinity or plus infinity. You can write both symbols. When the value of f of x grows arbitrarily large and positive. In other words, it's exploding near A. So when x gets sufficiently close to A, it is exploding and also positive. And in symbols, we write simply that the limit is equal to infinity. The next definition is basically the same, just changing infinity to negative infinity. So what we have to change is to say negative. So starting here, we say that the limit of f of x as x approaches A is negative infinity. When the value of f of x is negative and arbitrarily large in magnitude, when x gets close enough to A. And I have a few examples in here. So I just gave you a crazy graph here. And there are basically 3 vertical lines that where we can see around which the function is exploding in size. This particular function here, if you look at it at the graph, f of -2 is defined to be 0, but the value of the function there actually does not matter. As you can see around the number -2, so if you look close enough to -2 and you look at what the graph is doing, you see that the graph is way up there and becoming larger and larger on both sides. So we say that the limit as x approaches -2 is actually plus infinity or just infinity. Similarly, if you look around 0, the function is not even defined at 0. If you look here, there is no value for, if you look at x equals 0, which means along the y-axis, there is no value assigned to 0, but that's okay. However, if you look around 0, if you look at what the graph is doing, you see that it's way down there and becoming more and more negative. So the limit of this function as x approaches 0 is negative infinity. Meanwhile, the limit around 1 is a little bit more complicated. Again, the function is not defined at 1, but we don't care about that. But if you look on the left side of 1, so for points x around here, the graph is very negative. And if you look at points on the right side of 1, the graph is very positive. So this limit actually does not exist. There is no single number or symbol like these that the function is approaching. However, it's also indicating to us that the concept of a lateral or one-sided limit is also going to be meaningful for infinite limits. So I hope this was a clear example, because now I just want to discuss one-sided limits. So again, I have a definition here. You should pause and copy this down. I'm not going to do a definition for each one of the possible cases of one-sided limits. You can have a right or left limit, and they can be plus or minus infinity. So there will be 4 different definitions. They are all similar to this one. So let's say, for example, we want to define what it means for a right limit to be plus infinity. Here's how it goes. First of all, you need to suppose that the function is defined on the right side of the point. So we're going to say defined for points x near a, such that x is larger than a. Okay, so you just imagine the point A on the x-axis, and we're saying that the values of f of x at least make sense on the right side of a, close enough to a. Maybe also on the other side, but we don't need that. So granted that, we say that the limit, or the right limit of the function as x approaches a, is infinity, or plus infinity, which is the same thing, when, again, the value of f of x grows arbitrarily large and positive, when x is sufficiently close to a and on the right side. And in symbols, we're going to use the same symbol as last time. For a right limit, we have a little plus as an exponent on the a down here in the limit symbol. And then I'm just going to say, similarly, you can define the other one-sided limits when they are equal to infinity or minus infinity. So another graph example here. Look at this crazy graph. I'm just showing you a lot of different behaviors that can happen here. If you look around this graph, there are 4 different locations around which the function is kind of exploding. First, let's look at this -5 here. Notice that on the left side of -5, in here, the graph is going down without bounds. So this is a case where we can say the limit of f of x as x approaches -5 from the from the left, is negative infinity. Meanwhile, from the right side, let me scroll back up. I'm showing you kind of an oscillating behavior just to show you that the way that a graph can go to infinity, it does not need to go like straight up. This kind of behavior right here is also possible. As long as it is going up, doesn't matter that it keeps oscillating like that. It's kind of hard to think of a function that does this, but they exist. But regardless, we can see it is indicated by the graph that it's growing without bounds. So this right side limit is actually infinity. And because these two were different, you can say that the limit does not exist. A similar theorem from last time when this should have been -5. But yeah, when the one-sided limits are different, the limit itself doesn't exist. Next, let's look around. I think previously I said there are 4 locations here that we are interested in. It's actually just 3 locations. If you look, the next one will be the number 5. What's happening here, again, if you are approaching 5 from the left, look up to see where the graph is. The graph is just exploding up. So we're going to say that the left limit at 5 is plus infinity. The right limit is one that we actually already covered last time. What is happening to the function? First of all, f of 5 is 3. That's completely irrelevant if you're talking about limits. I just want to keep repeating that here. This point here is indicating the value of f of 5, but that's irrelevant for us. If you want to understand the right limit, you have to take numbers x close to 5 but on the right side and look at the graph and see what it's approaching. It's approaching the number 2 actually. So yeah, this is a case where the right limit is not an infinite limit, it's the number. That can happen. And because of the two statements above, you can also say that the limit as x approaches 5 does not exist, because 2 and infinity are different. And finally, just to complete, here's a case where it does exist. If you approach 10, both from the left and also from the right, you'll see that it's exploding up. This graph might trick you on the left side. Initially, it looks like it's going down, but if you look close enough to 10, you realize it starts going up again. And then it keeps growing up without bounds. So actually the limits around 10, both on the left and on the right, indicated by this graph, they are plus infinity. And in this case, the one-sided limits are equal, which means the limit itself is also infinity. So that was our graph example. And as you are starting to study limits, the idea of limits, other than graph examples, the other type of very simple example that you see sometimes is using a calculator to guess a value. This type of problem is not actually what our focus is, especially on exams, for example. We want to actually compute them analytically, and we're going to be doing this later. But I just wanted to show this as an example, or to help us understand the idea. So I'm giving a kind of complicated function here, x cubed divided by e to the minus 1 over x. And we're talking about one-sided limits at 0. The question is saying use a calculator to guess the value. You would not see this type of problem, written like this on an exam, for example. But something related to that, where you don't have to use a calculator, might actually show up. But what is the solution here? I encourage you to pause the video, get your own calculator, and try to think about this for a while. But the solution is, if you want to understand a limit, plug in values. What you have to do is plug in the correct values. So for example, if you want to understand 0 from the right, you need to start plugging in numbers which are close to 0, but on the right side, which means positive numbers. Plug those in for x in the expression and see what the expression is doing. So I copied down some values here that I'm going to be writing on the screen. For example, if you plug in 0.1, to abbreviate this, let me call the function just f. And so I can say, for example, f of 0.1 is about 22. These are all approximate. I'm going to write it like this, squiggly lines. If you start plugging in numbers closer to 0, you see that it dramatically increases. 2.6 times 10 to the 37. F of 0.001 is about 1.9 times 10 to the 425. Wolfram Alpha can do this. Calculator, not so much. This is incredibly large. Why is this happening? If you think about this, think about the function. As x is very small, the numerator is trying to become small also, x cubed. The cube of a small number is small. But the denominator is also trying to get small. That's kind of harder to see, but it's true if you think of it this way. Because x is small, 1 over x is large. So you're taking each of the negative large number. Think of the graph of e to the x function, which looks like this. E to a negative large number is like in here. This is a negative large number. The value of the exponential is very small in there. So as I said, this exponential is also trying to become very small. So both numerator and denominator are trying to become small, but the one that wins is the denominator. Exponentials usually decay or increase much faster than anything else. So this one is the one that dominates this function, and having a small denominator means having a large fraction. That's why this is happening. Okay, but we don't have to understand any of that if they're just saying plug in the numbers and see what happens. based on these numbers here, we guess that this limit from the right is actually infinity. The function is exploding without bounds. Okay, and now the question was also asking about a left limit. So what we have to do is plug in also numbers very close to 0, but on the left side, which means now they're negative numbers. This is going to make a huge difference here. Essentially because now the -1/x will be a large positive number, making the exponential also very large. And if this denominator is large, the function will be small. So if you try to plug in numbers in your calculator now, you will see something like -4.5 times 10 to the -8, and then -3.7 times 10 to the -50, and then just actually 0. Even Wolfram Alpha cannot, I mean, it's not going to be equal to 0, but even a computer cannot see how small this number is. So we can probably guess the values are approaching 0. So this is not an example of an infinite limit. It's a finite limit, but it is infinite on the other side. So, okay, hope this sheds some light into the meaning of infinite limits. Moving on. This is another graphical example where they give you the formula of the function. It's a piecewise function, but they gave you the graph, so we don't really care that much about this formula. But this is just to point out to us that piecewise functions are usually going to be present in this topic. So they say this crazy function here is pictured below. Analyze the limits both from the right, from the left, and at the point. For the points 0, 1, and 2. We have 9 limits to analyze here. And here is the graph. I'm not going to be referring back to the function. We don't need the formula if we can see the graph. But this is a very easy question. Look at the graph. Around here is 0, 1, and 2. We just need to understand what the graph is doing around those numbers. So I hope by this point you will agree with me that on the, let's say, left of 0, it's going to infinity. On the right of 0, it's also going to infinity, which means the regular limit around 0 is also infinity. Even though f of 0 is 1, which is irrelevant. Meanwhile, if we analyze around the x equals 1, on the left side, please try to guess this answer or get this answer before I say it. What is happening to the values of f of x as you approach 1 from the right? If you look at this graph, it's tending to go down to this point with a y value of 1. So in other words, f is approaching 1. And now around on the right side, that's a case where the graph is just going down without bounds, which means minus infinity. And because those two one-sided limits were different, the limit around 1 does not exist. And finally, around 2, I'll write them up here so we can see. It's something that's very similar to what we have done already. The limit from the left is exploding upwards, plus infinity. The limit from the right, here it is. The graph is just going down without bounds, minus infinity, which means the limit around 2 in general does not exist. All right, I just I encourage you to try to understand why the graph looked like this, taking a look at each of the pieces. For example, if you look at the last piece, ln of x minus 2 is just the graph of the ln x function, but translated 2 units to the right side. That's why you have this last piece here, for example. That's what it is. But okay, so all of these examples were simple. They were just showing us how to find limits by understanding what it means. But now we want to compute it analytically. You're going to see it's basically the same thing as computing limits when they actually are numbers. And all we have to remember is this remark. You should write this down very carefully. So imagine that you're studying a limit of a function f of x of this form, a fraction, g over h. When you're studying limits like this, first of all, an infinite limit can happen. It will happen when the denominator is going to 0, while the numerator is basically not going to 0 and also has a fixed sign. So we're saying stays away from 0 and doesn't change sign close to the number a. That should be believable. If the function in the denominator is approaching 0, that means the fraction in size is very large because you're dividing by a number that's kind of small. And then as long as the top is also not small, then this will be growing in size, either plus or minus infinity. So that's why we have to say the numerator stays away from 0. And then if that all happens, then in order to understand if it's plus or minus infinity, you have to understand the sign of the expression, both g and h, as x approaches a. So we're going to see examples of that. And finally, if it happens that the numerator is also going to 0, then this is called an indeterminate form. It's like 0 over 0. This could be really anything. So a more careful study is needed, which means usually simplify. We're going to see that. And similar remarks are valid for one-sided limits as well. So if you don't have x going to a, but actually a plus or a minus, it's the same remarks. So what do we have to take from here is when denominator is going to 0, that usually means the limit will be plus or minus infinity, but not always. Maybe if the numerator is going to 0 too, then you might not have that. Okay, so examples. Find the one-sided limits at 1 for this function, each dx minus 10 divided by x minus 1. And then the standard question, does the limit exist? We know how to handle that once we find the one-sided limits. So let's do this. Here's what you would normally write. If you're trying to understand limit as x approaches, for example, from the left of the function f of x, there's different ways to write this in symbols. This is all very informal, but as long as we understand the meaning. If you look at the numerator, no matter if x is approaching 1 from the right or from the left, each of the x is going to each of the 1, which is the number e. So you have e minus 10. And now what is happening to the denominator? It is going to 0. Just as x is going to 1, x minus 1 is going to 0. So you can write this symbolically to try to understand this better as like, well, you have to understand the sign now. That's the point. The number at the top is definitely not 0. But is it positive or negative? And in this case, it's negative. If you remember, e is about 2.7. So that minus 10 is negative. So you can write something like negative over 0. Or I've seen also professors who like to use this symbol, minus over 0. That's all just very informal to help us understand. So what happens here is that you need to understand also the sign in the denominator. In other words, as x is approaching 1 from the left, what is the sign of x minus 1? So just try to imagine, here's the real line, the number 1 is right here, and we're imagining x is on the left side of 1, approaching 1. X minus 1 is actually negative. Just think about it. For example, a number x could be 0.9. 0.9 minus 1 is negative. So a good way to write that like this, for example, just so you know, this is more like for yourself. This is your scratch work, for example. You're writing that this 0 in the denominator is a small negative number. And then you're good. You have negative over negative. That's going to give you a positive big number. How do we know it's big? Because we have a 0 in the denominator and a non-zero in the numerator. So this limit will give you a plus infinity. Now this is informal. If you wanted to write a formal explanation, you could write something like this. The limit, for example, first of all, of the numerator is a negative number. Negative number, and you can emphasize away from 0. It's a number that has a definite size, like -8, and away from 0. Meanwhile, the limit of the denominator, it is a 0 through negative numbers. This means as you approach 1 from the left, x minus 1 is going to 0, but it's also negative. Now, if you divide one of this, the first one by the second one, first of all, it is going to be negative over negative, which makes it positive. But second of all, it's also going to be growing in size because you have a non-zero number divided by a very small number. So the limit of one by the other is plus infinity. So this example has many of the ideas that we need. I'm going to be going faster through the other ones. The same example was asking now for a limit from on the right. What's going to happen? It's something changes now. E to the x minus 10 over x minus 1. Here's how you can write this informally. Again, the numerator is exactly the same analysis. Doesn't matter if you're coming from the right or from the left. It has a very well-defined limit of e minus 10. And the denominator also has a very well-defined limit of 0. But the difference now is that it's coming from the right side. So x minus 1 is a positive number. So informally, you can say this is equal to a negative number over a small positive number. And that it will be a minus infinity. Once again, minus, maybe I will color code this. Minus is because you have a negative over positive. And infinity is because you have a number over small number. More precisely, a non-zero number. We should have written that in here, probably different from 0, divided by a number that's getting closer and closer to 0. That makes the fraction larger and larger. So the answers were plus infinity and minus infinity, which means the limit itself does not exist. Okay, my plan for the rest of today, just a few more minutes, will be to do similar examples to this and then connect this idea to the asymptotes. Here's now an example where if you plug in at first, you're going to see that you have a 0 over 0, which means you have to be more careful. It's the same type of example. I have a function, and the number is -8 this time. Find both of the one-sided limits. In your solution, the first thing that you notice is the limit either from the left or from the right. Well, this is a t just for fun instead of x. We know that the letter that we choose doesn't really matter. But if you try to plug in t equals -8, the top will also give you a 0. Just think of it, 64 minus 48 minus 16, that's a 0. Indeterminate, which means it's not like it does not exist. Maybe it still does, but you need to be more careful. You need to just do something to simplify this first of all. And this is a very standard type of simplification right here. It is rational function. You can probably try to factor and cancel. So in the top, factoring the quadratic here, you're basically looking for two numbers with a sum of 6, product of -16. So that's 8 and -2. And now because we're talking about limits around -8, we can actually cancel one of these t plus 8. In other words, the t will never be actually equal to -8. It's just going to be close to it. So t plus 8 is never 0, which means you can actually do this cancellation. And now you're in better shape. This function, when you try to plug in -8, it's not 0 over 0 anymore. It is of the form that gives you infinite limits, which means a number that is not 0 divided by a number that is going to 0. And the only thing left to understand is the sign of these numbers. So now, for example, from the left, approaching -8, from the left, what is going to happen? First of all, upstairs, as t goes to -8, this is going to -8 minus 2, which is -10. A negative number different from 0. On the bottom, this is going to 0, -8 plus 8 squared. So as I said, this is a case that will definitely give you an infinite limit. You just have to understand the signs now. You already have the sign upstairs, which is negative. You need to understand the sign downstairs. Well, t plus 8 squared. Because of the square there, this is going to be positive. So you can say this is a negative number, different from 0, divided by positive number, and small, approaching 0, whatever you want to write here. This is the part that ensures you this limit will be an infinite limit. But positive is because of this square right here. And then, okay, what is negative over positive? That is a negative. So negative infinity. And because of the exact same reason, if you approach -8 from the right, basically nothing changes. You don't have to understand now that the t plus 8 will be positive. That's irrelevant because of the square. Whatever you have inside of the parentheses here will be squared, so it's still going to give you the same thing. Negative number, different from 0, divided by positive number, which is small. So that is also negative infinity. So again, the same reason for the positive. And now you see that the two limits are the same, which means the limit of the function is actually plus infinity. different from the previous example where it did not exist because the limits were different. So I don't want to extend this too much. Maybe I'll leave a few of these examples to the recitation. Now this is the last slide. I just want to connect this back to the idea of vertical asymptotes. So remark, you remember what we had mentioned before, a vertical asymptote is a vertical line that the graph is approaching from either side, at least one of the sides. So you can probably see that a vertical asymptote can happen if and only if, I mean, it does happen if and only if at least one of these limits is infinite. So either as you approach A from the right or from the left or both, if at least one of these you find a plus or minus infinity, then that means x equals A is a vertical asymptote. So again, examples of graphs having approaching vertical lines like this. You can see that it's always in the places where the limits are plus or minus infinity, at least from one side, like in this last line here. Only from the left, it would be a minus infinity. From the right, it is approaching a number, but at least one of them is minus infinity, so it is a vertical asymptote. Here's an example where I give you a function with a bounded domain between 2 and 4. And only the line x equals 4 is a vertical asymptote. Looking at the graph, you see that it is becoming vertical close to 4. But looking at the graph close to 2, it is actually not becoming vertical. It's approaching a number. So this line, even though I drew the line in dotted lines here, that's kind of bad practice. I should not have done that. It is not a vertical asymptote. So what you can see, this is useful to remember, vertical asymptotes can only happen at points on the boundary of the domain. In other words, it's going to be points where the function is undefined. However, it is defined at least close to those points on at least one side, like the number 4 up here. It is on the boundary of the domain. The domain stopped right there. That could be potentially an asymptote. In this case, it was. And similarly, the number 2 was also on the boundary of the domain. But in this case, that was not a vertical asymptote because of the limit. So just to show you again graphical examples connecting these two ideas of infinite limits and vertical asymptotes, and then that will be it. Here's the graph of ln of x minus 1. This has a domain of 1 to infinity, open at 1. And so you can see that 1 here is a point on the boundary of the domain. And in this case, the line x equals 1 is a vertical asymptote because, well, just look at the graph. The graph is becoming vertical there. Actually, the limit as you approach 1 from the right is negative infinity. Now the function square root of x minus 1, this has a similar domain, but now 1 is included. And if 1 is included, that means 1 is on the domain. So this could not possibly, x equals 1 could not be a vertical asymptote. The function has a value there. So it would not be going to infinity or minus infinity there. This limit is just 1. Right, so if the function has a value, if it is defined, then you don't have a vertical asymptote. And finally, an example where even though if a function is undefined, it does not have a vertical asymptote. The function in case now is x minus 1 times ln of x minus 1. If you want to graph this function using a computer, you will see it looks like this. So you see that even though the number 1 is a place where, like I described, on the boundary of the domain, it is not on the domain, but the domain is close to there. So even though that happens, the line x equals 1 is not a vertical asymptote. Why? Because this limit limit as x approaches 1 from the right, exists. In this case, it's a 0, as you can see from the graph. So because it's not infinity or minus infinity, then this is not an asymptote. So this will be it for this lecture. The recitation will be problems about actually computing these limits, just like this one, where we have to simplify the function and then understand the signs. Those are very important examples. So please don't miss the recitation.